can do is to subtract out old stars from this image, and you'll be left with young stars. Let's see. Old plus young, just young stars. Okay? So now what you have is that this is a picture of just regions where new stars are forming. Now if you look at it, again I'll go back again, old stars are distributed everywhere. They're like sort of here, there are dust lanes here. But if you look at just the young stars, they are distributed in a very thin, narrow line. What we try to do is to figure out, is to learn about galaxies based on how these young stars are distributed. Because young stars come from gases. Does it say something about gases? What's going on? So that's what we try to figure out. So before I start talking about how stars form, what nudges these gaseous clouds to form, let me show you, since I wanted to introduce observational astronomy also, so I thought I'll take you on a trip also with me to Chile. Most of these images that I'm going to show today and the previous one were taken from a 1.5 meter telescope, which means the diameter of the telescope is about 1.5 meters, located in Chile, in South America. And this is the mountain. And you can see that normally there isn't just one telescope on the mountain, but in fact there are a bunch of them. And this is a large telescope. This is a 4 meter telescope over there. This is the telescope that I was using. It was a 1.5 meter telescope. And this is a pretty picture in sunrise. And normally, the ideal place for an observatory is close to the ocean, but also very high. So kind of makes it difficult, but people tend to find these places. So in Chile, so here is an ocean actually about 2 hours driving distance from the mountain. And then we were at around 10,000 feet.
It makes sense that it should be high.
Right.
And altitude. But what does it
ocean does?
Ocean does.
Ocean stabilizes air. If air is coming over land, it would be very disturbed atmosphere. Whereas over the ocean, there will be a large portion where it will be extremely stable. So here is the picture in the morning, looking out from the observatories. So the observatories are here, and these are the Andes, and these are clouds forming underneath. In fact, they fill up these valleys. In fact, they just take the shape of these valleys going around. And in fact, they are so high that normally clouds form underneath us. And I've observed here during a thunderstorm. Again, the thunderstorm was underneath. You could see sometimes lightning flashes also, but everything was underneath, and above it, it was completely clear. So beautiful places, I mean amazing places. And down here. Now, the place where we stay is there is a dormitory on the other side of the mountain, a little bit below. In fact, this picture is taken from the dormitory. So there is a 15-minute walk in the morning.
How to separate the light from the star?
You mean on the telescope or on the actual images?
On the actual images.
It's just arithmetic. You can do mathematics on the images. You can. On the telescope, we use a filter. So it blocks out light from old stars. But we would like to isolate just young stars, but since you cannot make an infinitely thin filter also includes light from old stars, but it also includes light from young stars. That's how we do that. But there are small filters that blocks out light.
What kind of filter we use?
These are interference filters, just plain glass interference filters, isolated for that only that wavelength can go in. The rest of it is blocked out. And this is just a picture I thought for the people who have Volkswagens would appreciate it. But in the morning, when I was coming back one day, you can see they give you a key to this one of these cars, which you cannot take anywhere else because they cannot go anywhere else. But you can just drive from the dormitory up to the mountain. And it was always fun driving those. But anyway, now they have replaced those. This was 97. Now they have Toyota Cells. So it's not fun anymore. But anyway, this was just like a great picture. And there are other things also. Like for example, we have wildlife over there too. While walking back from the telescope, this used to sit over there on one side. And when I would be walking back, it would just go and walk to the other side and sit over there and didn't do anything. Yeah, it was almost like a pet coyote or wolf. small, tiny creatures called viscacho. This is a cross between a squirrel and a rabbit, and they like sunsets and sunrises. So if you want to find these guys, these are indigenous to Chile. If you find these, you can always find them on the side wherever there is sunset or sunrise. So anyway, so these are these creatures. Okay, so back to science. So here is, now I'm going to show you some images and to show you that stars form at different places. It's not always true that stars form in the same place. So these are all SA type galaxies, just one type of galaxy, but you'll see the diversity. So this is a galaxy, again, this is light from old stars. You can see a nice bar pattern, like stars are distributed in a bar and you have these rings. But when you look at the distribution of young stars, they're not distributed everywhere, but in fact, these are distributed in very particular rings. Okay? So that means that old stars are distributed everywhere. So that means at one time star formation was everywhere, or at least in different places. Today, snapshot, if you look at it today, today's stars are only confined to these rings. Here's another galaxy. NGC, by the way, is just New General Catalog. So it's object number 1022 in New General Catalog. It's not very romantic, so that's why I wasn't saying it was NGC 1022. Well, okay. But if you deal with hundreds of galaxies or thousands of galaxies, that's what you do. You don't name those. But anyway, so 1022, it has, again, old stars distributed in a large fashion. Young stars, nothing outside. Nothing is happening in the outer parts of this galaxy. Everything is concentrated in the central region. That's it. Everything is in the central region. Try to understand why is that. Here's another galaxy, NGC 7552. Again, we have a lot of dust in here compared to previous galaxies. It has these spiraloms. New stars. Wow, it's everywhere. You see, these are all the same type of galaxies, SA-type galaxies, large central regions with tight spiraloms. But when we look at where new stars are forming, they are forming like in different places. Now here, the reason why these regions are so bright is because they're very intense star formation. They are so bright that it's being overexposed. Now, we come back to the question of what is causing these stars to form in so many different places. The way it happens is you have this giant cloud, a hydrogen cloud sitting, and something needs to push it. Something needs to nudge it. And small portions of that cloud start collapsing. The question is, what pushes that cloud? Now, one possibility is that, and in some cases, the density of that cloud is so high that after a while it just spontaneously collapses. It's above some critical density. It just collapses. After a while, it just collapses. However, in these SA-type galaxies, the average density of these gas clouds was actually below the critical limit. So that was the reason why people thought that these galaxies do not have much star formation, because they cannot spontaneously collapse. So the question was, well, if they cannot spontaneously collapse, we do see star formation going on. What is the connection? What is pushing, what is nudging these clouds? So one idea is that interactions. Sometimes galaxies collide, and sometimes big galaxies eat up small galaxies. When that happens, you have a lot of chaos, a lot of disturbance going on, and perhaps during that time, these clouds collapse. That's what we think. In here, this thing caught our attention. Now, this is just a tiny blob you can barely see. The galaxy looks normal, nothing is going on much in the optical. But here is a blob sitting. Now this blob, we think, is a small dwarf galaxy. Much smaller than this, and it's sort of in an orbit around this, and it's going to be eventually eaten or disrupted by this large galaxy. Now our own Milky Way has eaten up a lot of small galaxies. In fact, right now, it's in the process of disrupting a galaxy called Sagittarius 4. So this galactic cannibalism, it's very common. We suspect that these type of things are causing disturbances in these gas clouds and for star formation. But the question is, do we have more evidence for that? For that, we turn again to hydrogen to look for signatures, but in a different way. Previously, I showed you the energy level diagram of hydrogen, and we talked about how the electron is being picked out and stuff. But there is a way to detect neutral hydrogen. Hydrogen where nothing is going on, just neutral hydrogen. Now, hydrogen is the simplest atom. So you have a proton and an electron, that's it. But both can have spins. They can either spin this way or that way. So there are two states, there are two possibilities. Either the proton have an upspin and an electron also have an upspin, or a proton have an upspin and an electron have a downspin. These are the only two possibilities. I mean, either way, look at it. Two possibilities. Both have parallel spins or anti-parallel spins. As it turns out, when both have same spins, either up or down, doesn't matter. When both have same spins, it's a slightly higher energy level compared to when they have opposite spins. And again, whenever something goes from a higher energy level to a lower energy level, it radiates. It gives off energy as light. Again, we can detect that. So if in space, due to collisions or whatever, the spin changes, they both go parallel. After a short while, it's going to go back to anti-parallel because that is the ground state. When it does that, it emits light at 21 centimeters wavelength. Previously, I was talking about 656 nanometers. Okay, so you have a meter, and then you go a billionth smaller than a meter. That is a nanometer, 656 nanometers. Here, I'm talking about a wavelength of 21 centimeters, much bigger than that. Or in frequency, it's around 1420 megahertz. You can almost tune your radio to it. You won't get it, but you can. And this is in radio waves, since 1420 megahertz, as I mentioned. So for that, you have to go to a different place. So this is the very large array in New Mexico, in the US. And these are individual radio dishes. This particular telescope has 27 dishes, individual dishes. And in fact, these are railroad tracks. They can change the formation of these telescopes. In fact, this is the closest formation, but you can also change it so that these telescopes are spread over 2.7 miles. So you can like really bring them close or bring them far, depending on what kind of work you're doing. We used it in the closest configuration. And for people who have seen Contact, this is the most famous radio astronomer. Okay, all right, so what do we find? Why we are looking for neutral hydrogen? Well, as it turns out, when galaxies interact, when galaxies collide with each other, it's still difficult to pull out stars from the other galaxy, but it's much easier to pull out gas. It's easier to pull out gas than stars, and gas takes a much longer time to relax, to go back into its fluid nature. So if something has happened to a galaxy, remember the galaxies that I've shown you looked normal. I mean, they didn't look like completely chaos. They looked normal. So we know that their stars are not doing anything funny. Their stars look okay. But if something is going on, if our theory is correct, that we see a lot of star formation because of interactions, we may be able to find those interactions in neutral hydrogen, in hydrogen gas. That's what we are trying to do. So here is a galaxy, NGC 5915. Again, old stars, a lot of young stars forming. Okay. So we look at a neutral hydrogen, and this is what we found. Wow. The grayscale in here, the picture itself, is optical picture, just visible. But these contours, these are of neutral hydrogen. This is mapping the gas. And this galaxy is here. So we are seeing this image up here. But what we find is that it is connected, even though the stars are not doing this, is the stars. There, those we don't see anything. But gas, the contour, it is connected with another galaxy down here. But and another galaxy down here. So it seems that even though the stars are not doing anything or doesn't show anything, but if you look at hydrogen gas, they seem to be interacting with each other. Gas from this galaxy and this galaxy, they are sharing these gas, and also from this galaxy. Even though these galaxies are located very, very far away, the hydrogen is still interacting. So perhaps This is what's causing the disturbance to these gas clouds. And this is the evidence in terms of neutral hydrogen, because we know it from there. Let's look at another one. NGC 3885. Again, this is the light of old stars. Again, look at completely normal galaxy. You don't see anything funny going on. Under normal circumstances, I won't show you this image because it's so boring. And here is the young stars. And again, the funny thing is, all of the star formation is just in the central region. That's it. Only in the nucleus, nothing outside. So we looked at neutral hydrogen with the radio telescope, and again, this galaxy is in the grayscale, and the contours are neutral hydrogens. And you see this funny tail, funny shape, going in this direction. That means this kind of shape, that something has gone close to it, and that object's gravity pulled out hydrogen from this galaxy. Not the stars, because stars look okay. But it managed to pull out just the gas from this galaxy. Yeah. So this is, now what was that? Now we could not find, this galaxy is really isolated, there isn't anything nearby. So we could not figure out another galaxy here. So we don't know which galaxy went by. Perhaps there was a galaxy that was moving very quickly and it went past it, and now it's a long time and the gas is still there that we can see the signature. Or perhaps maybe a small dwarf fell into this galaxy and left a signature. That's also a possibility. But it has to be very small because the stars are completely normal. Nothing happens. So if a big galaxy collides, it will disrupt its shape, the stars. But it must have been a very small galaxy, so we don't know. Although we do see a very small gaseous cloud, a big, small dwarf cloud that is right next to it. But we don't know if this is responsible for it or not. It's unlikely because it will have to go on a very big orbit to be here. But anyway, that's what we see here.
Salman, excuse me, there is no rotation of these objects which is causing them to relax or anything like that?
You mean for gas clouds?
Yeah.
But they do have rotation, but it is much stable. By rotation itself, they won't let these gas clouds collapse.
So what about shockwaves? Is that another candidate?
Yes, but shockwaves are actually, the question is, how are these shockwaves produced? And then again, they go back that when you form new stars, young stars, they blow up. And when they blow up, they produce these shockwaves. So that's how it's correlated again with that part of it.
If new stars are produced by collisions after Big Bang, these do not have specific areas. But your diagrams are showing that there are specific areas.
Yes.
Collisions are never specific, they are
Right.
accidental.
But like for example, in a galaxy like this one, what happens is that the gaseous clouds, if you have collisions, they would, because of collisions, they would lose angular momentum. If they would lose angular momentum, sometimes the process of the loss of angular momentum is so efficient, the gas gets down to the central region before it could form stars. When it gets down to the central region, the density is very high, and then you can form not just a few stars, but a lot of stars. So in fact, in a lot of these interacting galaxies like these, you have these, what we call nuclear starbursts. Just in the nucleus, there is this humongous starburst, but nothing outside. But the reason for that is because the gas has been efficiently transported from the outer regions to the center before it could form stars. Here is another galaxy. It's a prettier picture. So here's the galaxy, the SA type galaxy, and way out. So again, this is an optical picture. And if you just look at this picture in the optical, you would see, three nice galaxies sitting by themselves, doing their own business. Nothing is going on. But when we look in neutral hydrogen, so this is again, now this is not the contours, but these are the colored maps. And you see, this is the central galaxy at the same scale actually. It is connected with this one out here. And these are again a gas stream going through. There is this cloud which you don't even see here. And then there's another galaxy up in front. They're all messed up. They're all interacting. Now, the question is, do these things happen a lot? As it turns out, yes. In the universe, collisions between galaxies are very common. This is a picture from the Hubble Space Telescope. And here is a galaxy, and it is ripping out. Now, this is an optical picture. This is a much closer encounter, and it's not only, so we don't know what the gas is doing, but here is a galaxy which is actually ripping out stars from another galaxy. And now, one thing I want to make clear, that when galaxies collide, you would think, oh, there would be a lot of collisions of stars. But actually, stars do not collide. Even in big collisions, stars do not collide because the distance between stars, between individual stars, is so much that if two galaxies collide, the stars will just pass through each other. But it's the gases, because gaseous clouds are bigger, it's the gaseous clouds that collide. But stars, you don't find. I'm just going to talk about, in a second, I'm going to talk about the future of the Milky Way. But let me talk about it here first. Here's another image. Again, a beautiful image. So this is the galaxy disrupting, completely destroying this other galaxy. And remember, these collisions, when these galaxies, sometimes they just merge into each other. It takes a long time. It doesn't even happen in one go. Galaxies come in, they collide, they go through the other galaxy, then they would come back in, a second round, a third round, a fourth round, and eventually they would collapse. So this is probably a second or third orbit that it's coming in. It takes about 1 billion years for two galaxies to completely merge. Before that, they would just go through. So think about if we were living in such a galaxy, that would be kind of cool. I mean, apart from all these stars exploding and things like that. Probably there won't be much light, but maybe right in the beginning we will see something. Okay, well, here is another fun galaxy. This is again an image from the Hubble Space Telescope. This galaxy, believe it or not, used to be a spiral galaxy. What happened? Well, one of these small galaxies, we don't know which one. One of these small galaxies went through it, perpendicular, right through the center. Now, it's just like if you drop a pebble in a pond. What happens? There are ripples that are big. Same thing happened here. One of these two galaxies went through the center and it produced ripples. The angle was just perfect. It was completely perpendicular. And it produced ripples. And remember, what are these ripples in gas doing? They would produce stars wherever that ripple is. And in fact, today, the ripple has gone out and you are forming stars right over here. Because that's where the gas compression is going on. You see,